tends to be more practical.
Well, you say a couple of words about this. Homework. So, right, so what I want to accomplish in this homework is we're gonna kind of, I'm gonna tie up some loose ends, so I made a bunch of promises to you, do all that up at your house. First one's kind of, a fun one, show that if P and Q are projective R modules, that the tensor product of those, two projectives is still projective, which is kind of an important result. So, and now I've got a problem too, it's kind of, it's a 15-point problem. I've broken up into what I hope are kind of bite-sized pieces. So you all saw localizations probably in 8510, rings and fractions, right, where you have R over set of denominators, you all did see this, right? At some point. Well, you can generalize this to modules. So if you have an R module N, the set S inverse N, you can think of as fractions, N over S, where the numerator is in the module and the S is in this multiplicative set of the ring. And you add the fractions, I think the way that you think that you would, right? N1, S1 plus N2 over S2 is that thing. And notice the denominator, S1, S2 is still in that multiplicative set in R, and the numerator is still in the module. And multiplication by R is what you, it's 2. And remember, we declared two such fractions, N1 over N2. I'm sorry, N1 over S1 equals N2 over S2 if and only if there's a T in S such that T times the cross multiple, right? S2 N1 minus S1 N2 is equal to 0. I don't know if you remember that from localization, but that's what you have to do in general with 0 divisors, since there's a T that multiplies that cross multiple and gives you 0. You're not even going to have to worry about that extra condition here because in this problem, I'm talking about integral domains. And so basically what it means for those two to be the same is the cross multiple 0. The cross multiples are the same. So let R be an integral domain and N be an R module and S inside R multiple set. Show that every element of R localized at S tensored with N can be written as a single tensor, and not only that, a single tensor of this form, which is kind of cool, right? So in other words, you can almost think of an element of this as sort of 1 over S times N, loosely speaking. Show that there's an isomorphism between RS tensor N and S inverse N as reported above.
RS.
I'm sorry?
RS, what's that?
R localized at S is, that's the localization that, now tell me if you didn't see that. Well, this is what you may not have seen what I have written up there in red, but probably what you did see, I hope, in 8510. This. And maybe these are synonymous. Right? Did you see it with this notation?
Yeah.
Okay. Okay. Number 3, show that a tensor of the form 1 over S tensor N is, show that this is a 0 is 0, if and only if there's a T in S, just a T in. So that's a convenient way to tell if a single tensor is 0. And since every element of the tensor product is of this form, then that's kind of convenient. Number D, show that R localized at S is actually a flat R module, right? And all the stuff up here will probably give you do that. And finally show that Q is a flat Z module, which probably should follow from something earlier, that is in fact not projected. So this gives an example of a module that's flat, but not projected. Number 3, I think I showed you how to do A the other day, so there's 5 3 points. Show that if you have TM, which is the well, so R is an integral domain with a quotient field K, M is an R module, and TM is basically sort of the collection of all torsion elements. We know that TM is a submodule, show that M mod TM is torsion free, and show that when you tensor any module with a quotient field R, then it's the same thing as tensoring M mod T. So in other words, tensoring with quotient field kills out the torsion. And number 4, I promised you this one, the adjoint associativity problem. Show that if R is commuted with identity, and A, B, and C are R modules, then there's an R module isomorphism from home R, A tensor B, comma C, to home R, A, to home R, B, C. To me, the toughest part of this is just kind of wrapping your head around the way the math works. Once you figure out that, showing it's an R module homomorphism is probably pretty straightforward. My advice to you on this problem is don't just have one R module homomorphism, shows one-to-one and onto. Construct that in the inverse and show that they compose in both directions of the identity. I think that's really kind of one of the easiest to do. Any questions? All right. Well, that should be a fun one, I hope. And we will now continue with our adventure. Yes. So we had just gotten to this business of trying to apply apply modules over a PID to decomposition for linear transformation. Well, both A, B, are A. So what I mean by here are n by n matrices over F. Yeah, there exists P that P is invertible and now how many of you have seen before you've seen this notation or this notation before, you've seen this equivalence relation, right? It's pretty easy to verify that. Certainly A is similar to itself. You can just take the identity element. You can reverse the role here by conjugating B. If P inverse A P is B, then P inverse C A, and transitivity falls also. So let me give you kind of a theorem here. Theorem. So suppose what we have is E is an n-dimensional vector space over K. Dimensional vector space over K. Let's say phi from P to E is a linear transformation. And I think we'll call A is an n by n matrix. Okay, so we have some finite dimensional vector space, n-dimensional for K. We have some linear transformation, phi, and we have some A here. Here's what I want to say about this. Number one, there is unique monic polynomial. We'll call it P sub phi in Kx. Such that P sub phi of 0 so when you plug the linear transformation in, you get 0. So what do I mean by this? I mean, when you, well, actually, I'm just gonna write this down. I'll hopefully clarify this later. And P sub phi divides F for all F in Kx, for which F of the 0. And then I'm gonna make, so that's a statement about the linear transformation. I'm gonna make almost the identical statement about the matrix. Two, there exists a unique monic polynomial P sub A in Kx, such that P sub A of A is 0, and P sub A divides F for all F in Kx, for which F A 0. So that's the exactly analogous statement about the matrix. And three, let's connect them. If A is the matrix for phi, that is the matrix that we represent phi with relative some basis for E, then so let's let given or alternatively. So this is basically the linear transformation, just reverse coordinates, right? What's the polynomial here? What's that?
X2 minus 1.
Yeah. So consider, the matrix A be 0, 1, 1, 0. What is A squared? It's the identity, right? So A is a root more properly, say A squared minus the 2 by 2 identity. What about phi? Well, what happens if we consider what if we consider this transformation b squared minus the identity? What does this do to x, y? This is phi squared xy minus xy, right? But this is phi of yx minus xy. Go from here to here, I just applied phi once in the first coordinates. Now apply phi again in the first back. So that's what I mean by sort of plugging in the linear transformation, right? You just compose powers of the linear transformation and add it up point-wise, and that's what you get, right? And of course, maybe we're more familiar with multiplying and adding a matrix. Right? Now, what I haven't shown you yet is that this is the smallest. Now, by the way, I'll give us the answer of x squared minus 1. Where do you get that? Why? I know you know where you got it. Anybody else know where you got it? That's right. Right. That's exactly right. He sort of did the characteristic quality. I mean, I shouldn't speak for you, but I think you did the characteristic quality. Evaluated that. What about what if we had had so my matrix here everybody agree with that? That's for the identity would. But would your characteristic polynomial thing work here? Okay, why not? Oh, that's right. Because what is true is if you use the characteristic polynomial here, then these two things will be satisfied, right? But it won't be minimal, right? Because actually, what would the polynomial be here that we refer to? That's right, it would be x minus 1. We should contrast this with, for this one, the characteristic polynomial doesn't work because it's too big, right? But if we do this, characteristic polynomial does work, as it turns out. So you might see verify this, but this is look kind of familiar from the linear algebra days, this kind of thing. So let me point out before we kind of get in. So I'm going to give you a short proof here. This will be a useful observation, I think. Um. Consider following K vector space. Number one, here I have the, this is a K vector space. Let's take all n by n matrices over to the K. What is the dimension of this vector space? N squared, right? Because you can take the EIJ matrix, right? The matrix that consists of all zeros, but one in the IJ coordinate, that will be the basis, right? Two, this is kind of red herring. This is essentially isomorphic to this, right? This is also in square, right? These are all homomorphisms from E to E, and you probably know from linear algebra days that you can determine these by a matrix, right? That's a K too. But as in Sesame Street, one of these things is not like the other. What's different about this one? As a vector space, okay, this is, yeah, this is infinite dimension, right? Because basis one x squared x cubed forever and ever. That's an infinite basis. And this rather silly, simple observation will actually be kind of a linchpin in some. So let me go through a sketch and proof of this. Let's consider the map. From KX by the way, so I'm trying to go, my input should be a polynomial, like say F here. If I let me be a bit more explicit. My input's a polynomial here. I want this to barf out a homomorphism from E to E. And it probably should depend on this linear transformation. What's the most natural thing to do here? There you go. So just to be absolutely clear, I hope. So, yeah, f of x is k0 plus k1 x plus k E X E. Then F B, this is the linear transformation. K zero I. K one V, K two V squared. K. So here's my polynomial, here's my output linear transformation. I mean, it's just that pointwise addition of the powers. So where do I get my polynomial? Well, let's point out that so this is so in particular, kernel of this um, is a submodule of KX, and it can't be zero, right? It can't be zero because you're going from an infinite dimensional vector space to a finite dimensional. As kernel, uh, it's certainly, I hope it's certainly clear that when you have two things in the kernel of this, and their sum is in the kernel, right? And what about multiplication from K? Well, think about the way this math works. Notice that if, let's say G of X is in the kernel and little K of X is in K of X, then G of X, KX, G of X equals K phi G phi, which is zero. Because the G phi, or that the part of the linear transformation is zero. And there you go. So this, the kernel is an ideal. And what is the structure of KX as a ring? It's a principal ideal number. KX is principal. So the kernel is generated by some polynomial, which I will suggestively call piece of B, because you probably realize what's going to happen here. Let me look carefully at the statement. let's take P of phi to be this, why do we get uniqueness in this piece of phi? Because the mnemonic adjective, I mean, this is really not super important, but so any generator of this ideal varies by a unit from here. Now, the units are actually elements of K and KX. And so if you force the generator to be, or if you force the leading term to be one, then that makes that where the uniqueness comes from. Everybody okay with that? Notice that, of course, the zero, because it's in the kernel of this, and f of x and k of x is such that f of b 0, then f of x is in the kernel of this, which is the ideal generative of p of b. Therefore, p b the proof for part 2 is almost identical, and I'll leave 3 to sort of see if you can connect up why these two should be the same if A is the prefix for B. Okay. Questions? All right. So we say that, so I'm gonna use this terminology here, that piece B respectively is the minimal polynomial for P respectively A. And I can use the minimal polynomial if I demand that this is monic, so I get my uniqueness. Let me also remark that phi induces a KX module structure on E. KX module structure on E. Okay, so let me take a minute just to kind of underscore this. Now remember what E is, right? E is some finite dimensional, some individual vector space over K. Now, of course, there's a K module structure on that. It's a vector space, right? I mean, E essentially is n copies of K, so direct sum. How do we get this KX module structure? Well, this is the interesting thing here. So we've got not just a K module structure on it, but a KX module structure. So given finish it straight here, tell you how this works. Given some E and E and F and KX, then I am going to say that f of x operates on E by plugging in the linear transformation and seeing what it does to it. Because of course, when I plug in linear transformation to F, I get this, kind of new, bigger, fancier linear transformation. And just do its business to E, and that gives you an output of E, because this thing right here is a bigger, fancier linear transformation from E to E. So my input's E, and this output is such E. So that's how I get a polynomial to act on this. So now let me give you some definitions. So given this action here, we were going to say, okay, that a K subspace a K subspace F E. So really all I mean here is F is just a vector subspace of E, is said to be phi invariant if E of F is. So what it means to be phi invariant is the linear transformation. Actually, you can scramble stuff in F, but so a phi invariant subspace is like Las Vegas. What happens in Vegas stays in Vegas, right? That's what happens. So here is E, and here is F. What happens in a phi invariant subspace is everything in F stays inside of F. No leaving F, right? Might turn around like a washing machine. But if we have this, this is not. If it pushes anything outside of it. And equivalently, so this is kind of a good observation, right? F is a KX submodule of X. So notice that if phi of F always stays in F, then that's true for any power of phi of F. And so that means that if this is an invariant subspace, then that means that this is a K of X submodule, right? And of course, my second terminology, two, given your favorite vector V and E, then I'm going to tell you something called the V-cyclic subspace. Space spanned by the set V I V wait. It's called V-cyclic subspace. E, B, T, B, T, which is the span of B, I, B, I recommend 0. Is called a B six. Um, Notice that of course, this is kind of a setup. This is a special case. That is to say, note, if you have any cyclic subspace, it's being there. Because of course, when you apply theta, the set, you get the same set value, right? Well, actually, you get a subset of it back, I should say. Okay, so let me give you a theorem, which is basically a ripoff of consequence of what we did with modules over PID theorem. Theorem 17. Let phi be a linear transformation from E to E. Transformation of a finite dimension vector space over. Okay, so number one, there are monic polynomials Q1 up to QT. There exists monic polynomials Q1, Q2, QT. KX. And phi cyclic subspaces let's call them E1, E2, E, and E, such that E is the direct sum of these phi cyclic subspaces. With each QI, the minimum polynomial of phi restricted to each I. The minimal polynomial of B EI. EI. And this sequence of polynomials is uniquely determined by E and phi, as is the monic polynomial. Number two, let's see if this is better. There exists monic polynomials P1 to PS. And KX in and phi subspaces. Vij. Where here we have I between 1 and S, and J between 1 and KF. So the first index notes the polynomial that it corresponds to, and each one goes up KI, such that EI is equal to is sum I equal 1 S sum J equals 1 KI of Bij. What's that? Oh, so for each, so think of it this way. So for example, for P1, you have V1J, and how far can J go? Up to K1. So these are just the upper bounds for each one of these. Right? So think of these as relatively prime polynomials, P1, P2, etc. So you have a collection of vector spaces for P1, a collection of vector spaces for P2, and so forth. And the J's basically are how far out you go. Right? So, for example, yeah, better. So what this is V1, 1 direct sum, V1, 2 direct sum, V1, K1, and then you start over for the next vector space. V2, 1, V2, 2, and how far do I go? In the second step, I go K2, and so. And for all I, there exists M1, two, K, or case of I. Actually, I want to replace this. Actually, the last one should be strictly greater than 0. Such that P(I)(Mij) is the minimal polynomial. Minimal polynomial. of the restricted, linear transformation Bij. Okay. And again, these are uniquely determined. This list of primes and these lists of numbers here. Now, this might look familiar to you. This is actually the invariant factor. Decom. And this is the elementary class. Remember, when we decompose polynomial or modules over PID, we have those two different, and notice these are all torsion modules. There's no free part to this, because these are all, it's a finite dimensional vector space. So this is the analog, the invariant factor in the elementary divisor. This is a cool theorem. Think about why this connects, and next time I'm gonna really get my hands dirty. I'm gonna do a lot of kind of numerical examples for how you actually use this. But think about that, and that'll kind of help us be smooth next time. Any questions on that?
The KIs are just in natural numbers that exist.
Yeah, that's right. They're just upper bounds for every K. Other questions? Yes.
About the mononomial, one of the previous years, is there is it bounded in terms of the degree? Because I think you cannot have like degree in square, because then it will generate the whole ohm from degree.
Yeah, so the monic polynomial, so you're going from like, so the monic polynomial should be the kernel. I mean, it should generate the kernel of that linear transformation, right?
Yeah.
And so, your monic polynomial is going to be, well, yeah, I'm sorry, I lost the thread on what your question.
Yes, it's founded by N because the characteristic polynomial.
Right,
I was thinking the same, like, it has an effect on the dimension of the image,
yes, it affects the dimension of the image, right? But of course, so what will happen, your characteristic polynomial will always be of degree n, if you're going from an n-dimensional space to n-dimensional vector space, right? But that minimal polynomial that generates the kernel is of degree n or less.
N or less, okay.
Right. So, okay, other questions? Well, seriously consider coming to the math magic talk. It's, Neil and Eliza are always quite amusing. It should be kind of a fun one. So, great way to kick off the weekend. Otherwise